This is section 8.3, the converse of the Pythagorean theorem. Remember, the converse of a theorem just switches the hypothesis and the conclusion. And if the original statement is true, the converse is not necessarily true. It doesn't have to be true. It turns out that the converse of the Pythagorean theorem actually is true. So, let's remind ourselves of what the Pythagorean theorem says so that we can understand what the converse says. The Pythagorean theorem says in a right triangle, the square of the hypotenuse is equal to the sum of the squares of the legs. So if you have a right triangle, the square of the hypotenuse equals the sum of the squares of the legs. The converse says, if you have any triangle, and the square of one side of a triangle is equal to the sum of the squares of the other two sides, then the triangle is a right triangle. We can't call them hypotenuse and legs if we don't yet know that they're a right triangle, so that's why we don't use that in language. That's why we don't use those terms. We just say, if we take the square of one side of a triangle and it's equal to the sum of the squares of the other two sides, then in fact it satisfies the formula of the Pythagorean theorem, and so it is a right triangle. So we start with a picture that is nearly identical to the picture we started with the Pythagorean theorem, except that we don't know that we have a right angle. So I don't have any right angle marked on there. But in my picture, I know, I'm given this information, that when I take C and I square it, that's the same as taking A, squaring it, and B, squaring it, and adding them together. So C squared equals A squared plus B squared. I have to start with that information. I have to know that my triangle satisfies that formula. This converse then says, then in fact, it is a right triangle. Triangle ABC is a right triangle, where angle C, because it's opposite side C, would be the right angle. Instead of writing out a detailed proof, I'm just going to write down the key steps of the proof. First, we're going to draw another triangle. We're going to draw one that we know is a right triangle. We're going to draw a right triangle, we'll call it EFG, where the legs are A and B. I'm going to draw another triangle, and I'm just going to sketch it real quick here, so it's not going to look very good. But I'm going to draw another triangle where A and B, which were two sides of my original triangle, are now the sides, the legs, sorry, of my right triangle. This time I have a right triangle, and I've made it so that the legs are the same as the sides of my original triangle. So I'm not just drawing a random right triangle. I've drawn one where two of the sides are exactly equal to two of the sides that are in the triangle I'm trying to say something about. Okay, now how do I know I can draw a right triangle? Well, I can always draw segments of a certain length by the ruler postulate, and I can make a right angle by the protractor postulate. But we're just writing the key steps, so we're not going to bother writing down the reasons. Okay, well, that is a right triangle, and I'm going to call the hypotenuse D. If it's a right triangle, the Pythagorean theorem applies. And I know for sure that D squared equals A squared plus B squared. That's just the Pythagorean theorem, since I now have a right triangle to work with. Okay? I was given this equation, C squared equals A squared plus B squared. I was given that information. I know that's true about the top triangle. So that means D squared is A squared plus B squared, and C squared is A squared plus B squared. So it must be the case that C squared equals D squared, which is the same thing, equivalent to saying C equals D. Okay, and that's just substitution, because A squared plus B squared was both D squared and C squared. So C squared must equal D squared, which means C must equal D. Okay? But if C equals D, that means all three pairs of sides of my two triangles are congruent to each other. A is certainly congruent to itself, B is congruent to itself, and now C is congruent to D. That means my two triangles, triangle ABC and triangle EFG, are what to each other? Congruent. Good. They're congruent. They're not similar. Well, they are, in fact, similar. But they are congruent by side, side, side postulate. Because we now have all three pairs of sides equal to each other. Okay, well, if those are congruent triangles, then I know that angle C in the top triangle is congruent to angle G, because they correspond with each other. C, P, C, T, C, corresponding parts of congruent triangles are congruent. That means then that angle C is a right angle, because angle G was a right angle the way that I drew it. I drew it to be a right triangle. So if G was a right angle and C is congruent to it, C also must be a right angle. Alright? If C is a right angle, what does that tell me about triangle ABC? Well, triangle ABC now has an angle that is a right angle, so triangle ABC itself is a right triangle, simply by the definition of a right triangle. So I reached my conclusion. Triangle ABC is a right triangle, knowing that C squared equaled A squared plus B squared. So the converse of the Pythagorean theorem is true. It holds. Now the Pythagorean theorem is useful, but we can only apply it if we have a right triangle. And there are certain combinations of whole numbers, integers, that work in the Pythagorean theorem. For example, 3, 4, and 5 work in the Pythagorean theorem if I take 3 squared plus 4 squared. I'll notice that that is in fact 5 squared. 3 squared is 9, 4 squared is 16, 9 plus 16 is 25. 25 is the same thing as 5 squared. So 3, 4, and 5 are what is called a Pythagorean triple. Triple because there's 3 numbers, and a Pythagorean triple because it's a combination of 3 whole numbers that satisfy the equation c squared equals a squared plus b squared. Now they're not the only whole numbers that satisfy the equation. So we're going to list 3, 4, 5. Turns out that any combination of 3 sides that are in that same ratio of 3 to 4 to 5 also works. So any multiple of 3, 4, and 5 would work, like 6, 8, and 10. Because 6 squared plus 8 squared is 36 plus 64. 36 plus 64 is exactly 100, which is 10 squared. Similarly, if I take 3, 4, and 5 and multiply them all by 3, like 9, 12, and 15, those all satisfy, those together satisfy the Pythagorean theorem, because 9 squared is 81, 12 squared is 144, 81 plus 144 is 225, which is 15 squared. Similarly, 12, 16, and 20 works. If I multiply 3, 4, and 5 by 4, if I multiply them by 5, 15, 20, 25 works. I can multiply them all by 10, 30, 40, 50 works. Any combination of 3 numbers that are in the ratio of 3, 4, and 5. Any multiple, any constant multiple of the combination of 3, 4, and 5 would satisfy the equation of the Pythagorean theorem. But similarly, so does 5, 12, and 13. 5 squared, which is 25, and 12 squared, which which is 144, equals 169, which is 13 squared. And again, any multiple of those, for example, multiplying them all by 2, 10, 24, and 26, is also a Pythagorean triple. And I can multiply them by 3 or 4 or 5 or 206. Doesn't matter. As long as I multiply them all by the same number, I'll have another Pythagorean triple. Another one is 8, 15, 17, and also 7, 24, and 25. And again, I could take a multiple of those as well. Those are some common Pythagorean triples. You will want to know the ones that I've written in red. They will show up very commonly in this class and in trigonometry and calculus later. So what if it's not a right triangle? What happens then? I've got a triangle and my sides are still A, B, and C, where C is the longest side. So in order for any of these equations or inequalities to work, C must be the longest side of the triangle, because we're trying to see if C is the hypotenuse. We're trying to see if it is in fact the side opposite the right angle. So it's got to be the longest side to begin with, or it can't be the hypotenuse. So if we end up with the equation of the Pythagorean theorem, c squared equals a squared plus b squared, then by the converse of the Pythagorean theorem, C must be a right angle. It must be 90 degrees, and triangle ABC is a right triangle. So if we end up with that equation, c squared equals a squared plus b squared, then we have a right triangle, where angle C is 90 degrees. What if, instead of an equal sign, I have an inequality, where I know c squared is less than what I get when I take a squared plus b squared? Well, then angle C is not 90 degrees, because it was not equal. In fact, if c squared is less than a squared plus b squared, then angle C is less than 90 degrees. And ABC must be then an acute triangle, because all three angles will end up being acute. But if c squared is greater than a squared plus b squared, then angle C happens to be greater than 90 degrees. And triangle ABC then has an angle that's bigger than 90, which means triangle ABC is an obtuse triangle. So we can actually tell what kind of a triangle it is just by knowing the three side lengths. Here's an example of that. So the sides of a triangle have the lengths given. Is the triangle acute, right, or obtuse? Okay? So if my triangle has sides 5, 6, and 8, is it acute, right, or obtuse? So I want to see what happens when I take, the biggest one is 8, so I'm going to take 8 squared, and I'm going to take 5 squared plus 6 squared, and I want to compare those. 5 squared plus 6 squared is 25 plus 36. And what's 25 plus 36? 61. Okay, well 8 squared is 64. So 64 is bigger than 61. That means 8 squared is bigger than 5 squared plus 6 squared. If it's bigger, what kind of a triangle is it? It is obtuse. So it's an obtuse triangle, because we ended up with 8 squared being bigger than 5 squared plus 6 squared. How about an example number 2? Now I have the sides 20, 21, and 28. So I'm going to take 28 squared, I'm going to take 20 squared, and add that to 21 squared. Okay, 20 squared I can do in my head. That's simply 400. I'm going to get some help on the other ones. 21 squared is 441. And 28 squared is 784. Okay, well 400 plus 441 is 841. So 784 is clearly smaller than 841. It's less than, which means 28 squared is less than 20 squared plus 21 squared, which means it is an acute triangle. Okay, how about example number 3? What's bigger, 1, 3, or square root of 10? What's the biggest? Square root of 10 must be the biggest, because if I take 3 and square it, I get 9, which is not quite 10. So square root of 10 is the biggest side. It's weird to think of a side being a square root and not a whole number, but that's perfectly fine. Square root is a number. So I'm going to take square root of 10 squared and compare it to 1 squared plus 3 squared. Okay? If I square a square root, those cancel out, and I just get 10. Then I've got 1 squared, 1 times 1 is 1, and 3 squared, 3 times 3 is 9. So 1 plus 9 is 10. That is equal to 10. Last time I checked, those were the same number. So this actually satisfies the converse of the Pythagorean theorem, which means it must be a right triangle. Okay, you're going to do the exact same thing in your immediate practice problems. The sides of a triangle have the lengths given. Is the triangle acute, right, or obtuse? Do it the exact same way I just did in those 3 examples. And make sure you write down each of the problems and show me your work. Do not just write the answer. And that is the end of section 8.3.